Today we're going to take a look at radical expressions. Now we've seen radicals just briefly. We saw them very early on the first or maybe the second day of class. We're definitely going to go much further today. So the first piece that it talks about is saying, to recall, of course, that square root of 25 is equal to 5. But what is square root of 50, how, and why? So what happens when we have something that's not a perfect square, like 25 is that the square root of 50 is actually an irrational number. And it's actually the value 5 square root of 5 square root of 2. But we're going to talk about the why. So why is that the case? Well, the reason that that's the case, or sort of to prove or to justify that it actually works, is that if you take 5 square root of 2 and you multiply it by 5 square root of 2, just like what we did in the section with scientific notation, it's all multiplication, which means we can shuffle the order around. So I can move and I can shuffle and talk about just multiplying the 5s together first. So 5 times 5. And I can multiply square root of 2 times square root of 2. And 5 times 5 is 5. Square root of 2 times square root of 2 is 25. Square root of 2 times square root of 2 is 2. Square root of 4, which is 2. And then 25 times 2 is 50. So it meets the criterion for the answer because when I multiply it by itself, I get 50. That's why, okay? So as we're taking a look at these problems, that criterion has to be met in order for us to actually know that it's really the answer. However, that didn't really show you how the answer came about. I just proved to you that once I had the answer, it really worked. So we're going to work from square one on each of the problems instead and take a look at how we go about getting to the fact that 5 square root of 2 would have been the answer. So that's actually the first one we're going to do. We have the number 50. And as we work with these, what we're going to be doing is we're going to be factoring them. And there's several things that I could show you, and I think we're just going to stick with factor trees because most people are pretty familiar with them. So if I were to take 50 and I could divide it by something, somebody tell me a number that 50 divides by. 2 and 25. Fabulous. If you had done 5 and 10, that would have worked too. Totally fine. And there's the ability that I have right here to kind of stop and to play around with the fact that, hey, look, 25 is a perfect square number. But you don't always have that when you're breaking things down. So I kind of want to avoid that sort of beautiful thing that just happened there. Because if you had done 5 and 10, I wouldn't be able to use that fact. So what we're going to do is we're going to break them down until we get to prime numbers. So I don't have space here. I don't know why my slide is set up quite like this, but we're just going to shift it over so I do have space. 25 is then 5 times 5. So my prime factors are at the end. I have a 2, I have a 5, and I have a 5. Those are the prime factors. So my square root of 50 is the same as having square root of 5 times 5 times 2 in really whatever order you like. It doesn't matter. And since it's a square root, what we're looking for is we're looking for two numbers that match. And if two numbers match underneath the radical, then I can actually pull them out of the radical. And the reason why is because 5 times 5 is 5 squared, and square rooting and squaring are opposite operations. So this 5 can come out, and the 2 stays underneath. And my solution is then 5 square root of 2. 48, which is messier than the one I did before. So this one, we'll put it back underneath here now. I'm just going to do number 2 over here. We'll do 48. All right, so 48. Somebody tell me something that divides 48. 8 times 6. Wonderful. Okay, so let's break down 8. 2 and 4. 4 is still not prime, so we break it down again into 2 and 2. How about the 6? 2 and 3. All right, so we need to be a little bit careful to make sure that we capture the end of every one of the branches. So there's a 2 here, 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 another one here, and another one, and then a 3 over here. Those are all my pieces. So as I'm looking at taking a look at, writing these side by side, you kind of usually put the numbers that are alike together. How many 2s are there? 4. There's 4 of them. So I have 1, 2, 3, 4, and I have a 3. And like I said on the last one, I'm looking for pairs. So this is a pair, and this is a pair, and 3 is a loner. So the 3 is going to stay underneath where it was already, but each of those 2's that I circled in pairs will come out one time. So the first 2 comes out once, the second pair of 2's come out once, and the 3 is left underneath. So this is 4 square roots of 3.
Why is that? Why is it not 4 times 4? Like adding the 2?
Mm-hmm. Because this isn't 2 times 2 times 2 times 2 square root of 3. The 2's reside underneath the radical. So what literally is happening as we do that is that I have 2 times 2 is 4, right? And what's the square root of 4? 2. So the 2 comes out because the square root of that 4 joined together is 2. So it's like we're separating. We just don't need to write it all out that way. It's like we're separating it out like this. Actually, I think I probably put it over here. Square root of 4, square root of 4, and square root of 3. So the square root of 4 is 2, the square root of 4 is 2, and then the square root of 3 stays put. Let's do the next one. So part of the reason why I want you to think about these inside of pairs instead of like the square root of 4 business that we were looking at, which justifies why it works, is because this process works for variables as well. So on the next one, I actually have a variable raised to a power here. It's x to the 4th. So we're going to break down our 45. It's 9 times 5. And 9 is 3 times 3. So I have 2 3's and a 5. And I've got 4 x's. So 3, 3, 5, and then I have x, 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 and x. And I'm looking for pairs. So obviously I have a pair of 3's. And I have a couple of pairs of x's. So if I were thinking about it and wanting to show a little bit more work about why it was going to work, kind of like we did with that last one that we were looking at, this would be the square root of 9, the square root of 5, the square root of x squared, and the square root of x squared. I don't need you to show me that, but if it helps you to see it, then by all means go ahead and show that. The square root of 9 is 3. The square root of 5 just has to stay the square root of 5. But each of these that are the square root of x squared, what is the square root of x squared? It's x. So each of those that are circled in red is each individually x. And a simpler way to write that, of course, would be x squared. So if you're coming directly from this particular point of view, the 3 comes out, the group of x's each come out, and the 5 stays underneath, which will still result, of course, in 3x squared square root of 5. Number 4, 12 factors is 2 times 6, or you can do 3 times 4 is fine. And then you get 2 and 3. So you get 2 2's and a 3. And there are 3 y's. So we have a square root of 2 times 2 times 3. And then I have 3 y's. So somebody tell me one of the pairs that you see. Pair of 2's. Any others? Yeah, there's one pair of y's. There's still one that's left over, not in a pair, but there's one pair of y's. So each of those pairs that I found come out one time. So the 2 comes out one time, and the y comes out one time. But then the 3 that didn't have a pair and the y that didn't have a pair get left underneath. And we're done. Now, square roots are sort of the building block of radicals. They're the first radicals that you ever encounter. But there is a generalized form for radicals as well that makes it a little bit broader. Instead of just a square root, we can actually have what's called an index outside, and it doesn't have to be a square root. That n is called the index. This is actually called a radical, that symbol. And the value that's underneath the radical, which I've written there is a, that's called the radicand. Now, our default a lot of the time, and in all the problems that we've had before, is that there isn't a number written in the front, right? Where I have my little n, there's just something there's nothing there. So when that happens, that's what happens when we have n equal to 2. So when n equals to 2, we have this. It's actually the 2 where the index is. But it gets shortened to simply square root of a. So when you don't see a number out there, it's an understood 2. It's kind of like when I see the variable x just written all by itself, it has an understood coefficient of 1, right? Even if you don't see it, you know it means that it's 1x. Here, if you don't see the 2, it still means it's a square root. Any other index will be expressly stated. So if we're dealing with a cube root or a fourth root, it'll say so. But if it doesn't say anything, then it's a square root. So when we look at the next example, you in fact do see that. You see an index on the first one right here, number 5, of 3. What does it mean? Well, it means that just like before when I was looking for pairs because it was a square root, now I'm going to be looking for triples because it's a cube root. The index tells you how many have to be in the group for it to be able to be removed from the radical. So as I'm looking at 16, 16 is 4 times 4, and the 4s are 2 times 2. So this is actually the cube root of 4 2s. Now, if it were the square root of 16, you'd know that that's just 4. It is not the square root, it's a cube root. So you're looking for a group of 3 identical pieces. And there are, in fact, 3 2s. There's more than that, but there's 3 that we can put in a group together. So those 3 in that group with the cube root index outside, that 3 will come out one time. The other 2 will stay underneath, and the radical will stay where it is, and it needs to have the cube written in the spot where the index should be. Right? It has to have that 3 written there, otherwise it's an understood square, and r simply isn't a square. So it's 2 cube root of 2. So I'd like for you to take a second and to break down 256, and then we'll make sure that we all have it broken down and worked out well. Take 256 and take a calculator with you real quick. And attempt to break down 256 into some numbers. Give it a shot. I don't think it's 25 and 6. No, not like that. They're not just beside each other. 16 is a number that works. What is it? Somebody said. No, it doesn't. That's what it would be if it were a square root, but we have a 5th root, Trinity. You see that little 5 there? Yeah. That little 5 is going to make a difference. Okay, so how did you break it down first? Do you want to try to guide me through what you did, Jenna?
I kind of just was dividing it by numbers.
Okay, what's the number you divided by that worked?
I divided by 8.
You divided by 8, okay.
Although
So
I started with 2 and kind of just tried to get
bigger numbers, yeah. 2 definitely works because it's even, right? Sure. So if you did it with 8, what was the counterpart that it multiplied with to give you 256?
32.
32. Lovely. So this is a good place to start. How will 8 break down? 2 and 4, you betcha. And how about 32? 8 and 4. Now we're going to keep breaking things down until they get to the prime numbers. Right now I have several things that aren't prime. 2 is fine, but 4 breaks down into... And then we have another 8 over here. 2 and 4. And there's that 4 again. Getting a lot of 2s, aren't we? And then my last 4 over here is another 2 and 2. Are they all 2s? They are. How many 2s are there? Whew. 8 of them? Good night. All right, so as we rewrite this, we've got a fifth root, so that's my index, right, the 5. And we have 1, 2, 3, 4, 5, 6, 7, whoops, and 8 2s. That's what y'all told me, 8 of them. How many need to be in a group to come out from underneath a fifth root? 5 of them. That's 5 of them. So I'll pull that 2 out because it's underneath there 5 times. And then I have the fifth root of whatever remains. So what remains is not enough to pull anything out, but it's 2 times 2 times 2. And what is 2 times 2 times 2? It's 8. So I end up with 2 fifth roots of 8. Okay, the index is really important. It tells you how many have to match, how many you're looking for. We talk about like terms a lot. We use them for different kinds of things. This one has a definition of like terms as well. So like terms, when we're talking about radicals, means that they have the same index, right? So like the last one's index was 5. And they have to have the same radicand. So the radicand means the number under the radical. So they have to be a lot alike to actually be able to combine. So for instance, back on here on the first slide where I had the numbers 1 through 4, they all have an index of 2, right? Because they're all square roots. But none of those underneath, right, the radicands are the same. So since the radicands are not the same, I can't combine them, even though the indices are. So let's take a look at some where we maybe are able to combine some things. So on number 7, you'll notice that what type of index do I have on both of the terms? Yeah, so there's term 1, there's term 2. They aren't written in, but they're an understood 2, right? They match. And the radicand on both of them is 3. Right? They're 3 underneath the radical. That makes these like terms. So I have 6 of these square roots of 3 minus 2 square roots of 3. How many square roots of 3 am I going to have? 4. So it works just like anything else with like terms. We're able to then subtract or add, depending on what we're working with. So I have 4 square roots of 3. What do you notice about number 8? What part's not the same? The radicand. Yeah. So the index is the same, right? Okay, so that's good, because if the index is not the same, there's no chance in it working. The radicands don't match, but the actuality is that the radicands are not in simplified form either. Do you recognize that? Right, the numbers are kind of large underneath. We at least stand the chance of being able to factor them and reduce them and bring something out. So that's where we go next, is to see if maybe there's a way to get what's underneath the radicals so that they do match. So we're going to break down 18, 9 and 2, and the 9 will be 3 and 3, right? So on the first piece, I have the square root, oh, there's a 2 in front of it, so sorry, 2 of 3 times 3 times 2. On the next one, 27, how does it break down? 9 and 3. My 9 is another 3 and 3. So I have plus 8, and I have 3 3s underneath. So far, so good? How many need to be put into a pair to come out? 2, because I'm dealing with a square root. So here's 2 3s. So it'll come out with the 2 that's already here. It always comes out multiplied by what's next. Okay, so the 2 before will get multiplied by the 3 I'm bringing out. And then there's a 2 left underneath. How about in my second one? There's a group of 2 3s, right? So that 3 can come out as well with the 8, multiplied, always multiplied. And there's a 3 left underneath. Now, the radicands still don't match. But now we can know for sure that they don't match because we've simplified them to try and see. We do need to go ahead and multiply each of these things together. I do not know why I wrote 24 there. I was already multiplying in my head, so sorry. That's a 3. It is a 24 here in a minute. So I have 2 times 3. So I have 6 square roots of 2. And then the 8 times 3 I was trying to do before, the 24 square roots of 3. And I don't have any way to combine them because square root of 2 and square root of 3 have different radicands. All right, so there's a very helpful rule for products called, or for radicals called the product rule. And the product rule says that if I have the square root of a number times the square root of another number, they don't have to match, right? So A and B could be different. And I've got the radicals multiplied. The indexes have to match, right? So they both say square root here. We could put them in general to both say nth root. We'll do that just for the sake of having done so. Then what we're actually allowed to do is we're allowed to multiply the A and the B together and then do the radical afterwards. And that's really helpful because sometimes you can't simplify an individual radical, but if you multiply 2 individual radicals in their simplified form together, their product might be able to be simplified. But the indexes have to match. So for instance, if you take a look at this first one, I have square root of 3 and I have square root of 5. They both have the same index, right? So this is going to be the square root of what? 15. Now it doesn't reduce, but it still looks a lot simpler than square root 3 times square root 5, right? It's a shorter version of the same thing. Now this one's a little bit different, not in the sense that it doesn't look simpler if I simply multiply them. 6 times 15. Do you know what 6 times 15 is?
90.
What is it?
It's 90.
It's 90. Okay, so square root of 90 looks better, and that's fine. But square root of 90 is able to be simplified. Okay, so here's the kicker, though. It's probably not so helpful to have multiplied it to get you the square root of 90. It's okay. It's not a big deal. But if you notice that the 2 numbers that you're starting with already have factors, you might want to go ahead and just do the factors to begin with. So you notice that this is a 2 and a 3. This one's a 3 and a 5. So over here, instead of getting to the square root of 90, we can do the square root of 2 times 3 times 3 times 5. If you get square root of 90, it's fine. You're just going to have to factor 90 in. It doesn't really matter. It's just that you're working with a bigger number to start with on the factoring. Sometimes it's easier to work with smaller numbers on the factoring instead. So is there a group of 2?
No. Yeah.
Yes. There's 2 3s. Yeah, there's 2 3s. So the 2 3s will come out as 1 3. And what remains underneath the 2 and the 10, I'm sorry, the 2 and the 5 give me the square root of 10. Okay, so if you get 90, it's not the end of the world. You just factor 90. But sometimes it's easier to factor smaller values. Yes?
What do you do if you get 2 pairs?
Same thing. You just pair them both up. So like let's say at this point, different problem, but let's say at this point you got 2 times 3 and you have 3 times 2. Then you would pair your 3s together, you'd pair your 2s together, and you'd bring them both out. There would be no more radical because there'd be nothing left underneath it. Yeah, and you can do that. I mean, that can happen. Sure. All right. This one has the variable z underneath. Still the same indexes, so I can still do the operations that I'm wanting to do. The 5 and the 2, though, much like the first one on this page, or this slide, they can't break down, right? Just like the 5 and the 3 couldn't. So I don't have to do anything like I did on 10 because there's nothing that can be done that way. So I'm simply going to put them underneath, and the 5 and the 3, of course, can be multiplied to 15. But I do have 2 z's, and so those are actually in a pair, right?
Wouldn't it be 10?
Oh, I'm sorry, I was thinking the 3 from before. That's that zoom in, zoom out thing. There you go, out of 10. Yes, thank you. So I have 2 z's, right? So here are my 2 z's. They're in a pair, so what's going to happen with them? They're going to come out as 1 z, and then the 10 will stay underneath for the square root of 10. Okay, so far so good. A couple more. These 2 are a little bit more complicated. The reason these 2 are a little bit more complicated is because I actually have distribution involved, right? I've got multiplication over a set of parentheses. So as I'm doing this, I'm going to multiply like this. So in a very real way, I have square root 5, square root 7, plus square root 7, square root 7, like that. Now, much like my 2 and my 5 on the last problem, or my 3 and my 5 on the first one on this slide, the 5 and the 7 at the beginning here, the square root of 5, square root of 7, they don't have anything in common that can simplify. So they really are just going to be the square root of 35. Nothing I can do. But what is the square root of 7 times the square root of 7? The square root of 49, which is, yeah, so that's the square root of 49 if you think of it that way. Or you can think about the fact that you get 2 7s underneath the radical, either way. So what happens when you have either of those results? What do you get? Just 7. So I have my square root 35, and the other piece is just 7. And of course, they don't combine because they don't have the same index and radicand. In fact, one of them is a whole number, namely 7. We'll do the same thing on the next one. So let me write out what we have. We have 2 square root 5. And I'm just going to write it with the 15 underneath because we know that's the product rule anyway. And then plus. And then I have 2 times 3 and then square root of 5. So let me sort of hit on what I just did. The rule of thumb is that if the numbers on the outside, they get multiplied by the numbers on the outside. And if the numbers are underneath the radical, they get multiplied by the numbers that are under the radical. And the reason that I'm able to do that is because it is multiplication, and I can change the order around. So while this literally said 2 square root of 5 times 3, I simply switch the order because I'm allowed to, because that's a commutative property of multiplication. Because the 2 and the 3 can be combined, I'm actually able to multiply both of them together, so I simply set them together to show that. So on the first one here, how does 15 break down?
5 and 3.
5 and 3. So I'm just rewriting that. I didn't show a tree, but that's what I did. And on the other one, I have 2 times 3 to give me 6 square roots of 5. What's going on the first one?
It's a pair.
There's a pair. I have a pair of 5s. So this pair of 5s can come out, right? Pair of 5s comes out once. There's already a 2 out here. Now there's also a 5 out here. Again, anytime you bring something out, you multiply by what's in front. And you have the 3 left over underneath. We had 6 square root of 5 over here. 2 times 5 is 10. So 10 square root of 3 plus 6 square root of 5. And nope, still can't simplify them because the indexes, while they match, the radicands do not. One is 3 and one is 5. Any questions on that? That's the product rule for radicals. Okay, the next one is the quotient rule for radicals, and it feels very similar. It tells you that if you have the nth root of A divided by the nth root of B, you're welcome to divide the A and the B and then take the nth root. Or the other way around, whichever one's, I mean, they're equivalent. So whichever one proves to be most useful or helpful in a particular situation, you can shift to the other notation. So let's try one that has this in it, a very direct application. We have square root of 3 over square root of 75. So we're going to rewrite it as 3 over 75. And the reason that we might be so inclined to do so is because 75 and 3 have something in common. What do they have in common? It better be 3, since 3 doesn't have a lot to choose from, right? Now, what's 75 divided by 3? It's 25. So I can divide each of these underneath here by 3, right? It's a simplification of fractions. We've talked about that at length. So I end up with a 1 on top and a 25 on bottom. So square root of the 1 on top is what? Yeah, what's the square root of 1? It's 1. And what's the square root of 25? It's 5. And if you weren't sure, of course, you could just break it down, and you see the 5 and the 5 showing up. There's a pair of 5s. So this one doesn't have any radicals when we're done because it was a perfect square once I simplified the 3 and the 75. Okay, so far so good? All right, the next one has quotient information in it, but it doesn't have that quotient rule showing up as necessary, at least not this one doesn't. There's a really common mistake that students will make when they have a problem like this is that they will often recognize, hey, there's a 25 on top and there's a 5 on bottom. I'll just divide those two and I'll move forward. The problem is that the 5 that's underneath actually divides not only the negative 25, but also the 15 radical 3. It divides all of it. So if you're going to try to simplify this, it is most helpful perhaps to separate the fraction out. Now we don't usually do this with fractions this way because we're usually trying to merge things together. But in this case, we're trying to simplify the fraction. So I can separate each of the pieces that are on top to divide by the denominator 5. So what is negative 25 divided by 5?
-5.
Yeah, that one's negative 5. And then I've got the 15 square root of 3 divided by 5. So again, I recognize that there's a square root of 3 on top, but it's actually two pieces being multiplied on top. It's almost like having 15x over 15. Not 15, over 5, sorry. If you had 15x divided by 5, what would it be? 3x, right? You don't worry about the fact that, hey, there's an x there. What do I do about it being divided by 5? You don't have to because it's multiplied already by the 15. The same thing's true for my square root of 3. The only division that we have to worry about because it's being multiplied on top is the division piece that's outside with the denominator. So 15 divided by 5 is 3, and then it's multiplied by the square root of 3 that was already on top. Okay, so far so good. We have just a few more things to take a look at in this section. This is a varied section of material for sure. We have to deal with something called rationalizing. So we learned from the quotient rule that the square root of 3 over the square root of 5 is the same thing as square root of 3 over 7. I didn't say that right. The square root of 3 over the square root of 7 is the same thing as the square root of 3 all over 7. Right? That those are two forms of the same thing. Neither one's really simpler. I mean, there really is not like a preferable option here. They're both equally unhelpful in terms of I can't simplify any further. Agreed? They don't really look any better. But there are times when having a radical remaining in the denominator is not desirable. Okay? There are several places throughout other math classes that you will take, college algebra, perhaps a trig class or a calculus class where these things come back up and so forth. It just sort of pops up at these random spots in mathematics. So this idea of rationalizing is something we talk about here since we're talking about those radicals. So what we actually do is we're actually trying to not have a square root on bottom. That's really what we're trying. We don't want the square root of 7 to show up on bottom. And it doesn't help us to put all of it underneath a radical because then I still have a denominator that's underneath a radical. It means it's just the same thing. So what I'm about to do is not really simplifying. Be very clear on that. I'm rationalizing denominators. And it's not going to look simpler than the form we started with. It's going to look more complicated. It's going to look messier. Okay? So this is not simplifying. So what we do to rationalize the denominator when there is a square root in the denominator like this, an all by itself square root, like square root of 7, is that we multiply it by itself. Now, if we do that to the bottom, we have to do that to the top as well. Multiply it by the same square root of 7. But let's talk about why we want that. What is the square root of 7 times the square root of 7? It's 7. So I no longer have a radical on bottom. That's what it means to rationalize. Now I still have a radical on top. Right? I can't rationalize everything. I only get to rationalize the denominator. So on the top, I have the square root of 3 and the square root of 7. And then we're back to that product rule that we encountered several slides back. And what would the top be?
21.
Square root of 21. So again, this is not simpler than it was before. It isn't. But the denominator is a rational number now. And rational number means it's a simplified version that doesn't have a radical in it. So looking at the next one, number 17. While it's true that I could write square root of 3 over square root of 24, it's probably not the best way to start. Does anybody see another option here? What can you do with the 3 and the 24? You can simplify them. What do they both divide by? Yeah, they both divide by 3. So our ideal place to start here is to make what's underneath the radical smaller. So this is 1 and 8. Everybody good so far? Okay. Now, I'm going to go ahead and do the individual square roots. Well, the square root of 1, of course, is 1. That's the top. But the square root of 8 is not perfect. Right? It's not a perfect square. How will 8 factor? 2 and 4. We've done that one like, I don't know, 6 times today, right? And then 4 is 2 and 2. So it factors as having 3 2's. So over here, my denominator now has 3 2's. So I haven't gotten to the rationalizing the denominator part. I'm simply simplifying the radical that's down there. I have 3 2's underneath a square root. What can I do? Move a pair out. That's awesome. So there's a pair of 2's, and that pair of 2's can automatically come out, right? As 1, 2. So I now have a 1 on top still. Whoops. A 1 on top still. Have one of my 2's out, and I still have one of my 2's trapped. So far, so good? Okay, I've simplified as much as I can. This actually is a simplified version. It definitely is. But it's not rationalized. I do not have a rational number on the denominator. So now I'm going to do the same thing I did on the previous problem. The previous problem had a radical 7, square root 7 underneath, right, on the denominator. This one has a square root of 2. So we're going to multiply it by square root of 2. And if I do it on bottom, I have to do it on top. Now the top will still have the square root of 2, because 1 times square root of 2 is square root of 2. But what happens on bottom when I multiply square root of 2 times the square root of 2? You just get 2. Right? Square root of 2 times square root of 2 is the same as the square root of 4, and the square root of 4 is 2. So this one gives me a 2, and there's a 2 over here. So what does my denominator become? Actually becomes 4. And while it's awfully tempting when you look at this to say, I have a 2 on top and a 4 on bottom, and so I'm going to reduce, you cannot, because the 2 on top's underneath a radical. So it can't be reduced by something that's not underneath a radical. Okay? So resist the urge to simplify things that cannot be simplified. Square root of 2 over 4 is the reduced version of a rationalized number here. There's one other type of thing that can happen in our denominator that's less than desirable. Instead of simply having a square root or a cube root or something like that, we might actually have addition and subtraction along with it. So for instance, we might have something that looks like these. Not only do I have a square root of 3, but I have 5 plus the square root of 3. And our technique of simply multiplying by the square root of 3 won't work. Why won't it work? Well, because I would have to distribute the square root of 3 to each of the pieces 5 and square root of 3. So I wouldn't end up rationalizing it. So what we're actually going to do is something called multiplying by the conjugate. So when I have a number like a plus square root of b, okay, like the next one where it was 5 plus square root of 3, a plus square root of b, oops. The conjugate is the same thing, the a and the square root of b, but the sign is opposite in the middle. And I'd like to show you why, in general, that this is actually helpful. So when I multiply these by one another, okay, remember we're going to do first, outer, inner, last. It's a distribution process. So to multiply a times a, I get a squared. The outer one's multiplied, a times negative square root of b is negative a square root of b. On the inside, square root of b times a is positive a square root of b. In my last terms, negative square root of b times positive square root of b gives me a negative, and then it's just b. Square root of b times the square root of b is b. Just like a moment ago, the square root of 7 times the square root of 7 is 7. What do you notice happening in the middle of this thing? Yeah. These pieces add to 0. And that always happens. And the reason that it happens is because we did it by the conjugate. Like they did, that's how we created it to happen. We did it on purpose. It's not an accident, it's an on purpose. Okay? So we are allowing it to actually have the ability to eliminate the radical when we use the conjugate. So let's try one with some numbers in it. Number 18 would be one of those. You see that you have a 5 and you have a square root of 3, right? And they're added together. So what's the conjugate of 5 plus the square root of 3? Yep, 5 minus the square root of 3. But anything you do to the denominator, you also have to do to the numerator. Top and bottom, right? So let's actually work through the numerator. It's the one that will still have the radicals involved when we're done. So 2 times 5 is 10. Now I have 2 times negative square root of 3. What's that? I started you off, it's negative. Negative what? Not quite. 2 square root 3. That's it. I can't combine the 2 with the 3 because the 3 is under the radical and the 2 is not. So all I can do is simply write them next to one another. So it's 2 square roots of 3. Now the denominator, notice the inner and the outer terms, they're the same with opposite signs. So just like over here, they cancel by design. We did it on purpose. So the only terms that I actually have to multiply are the first terms together, namely, the 5 times 5, which gives me 25. And then the square root 3, the last terms, the square root of 3 times the square root of 3. One was positive, one was negative, but what's square root of 3 times square root of 3? You guys either know it and you don't want to say it because you think it's so obvious, or we're struggling still. 3. It is 3. When you multiply a square root by itself, it cancels the square root. Square root of 3 times square root of 3 is 3. The sign in the middle is subtraction because I multiplied positive times negative. And then we're going to see if there's any simplifying that can be done. We certainly can subtract the denominator. 25 minus 3 is 22. And the top is 10 minus 2 square root 3. So do you notice any simplification that can happen? So you can't do 10 minus 2 because it's 2 times the square root of 3. Order of operations. These two are connected with multiplication, so we cannot subtract the 10 and the 2. That's not going to work.
Simplify.
Okay, do you see a simplification, Harrison, that would work?
Put a 2 and a 10.
Yeah, so the 10, the 2, and the 22 do all divide by 2. So I can do that. It doesn't eliminate the denominator, but it does make everything a little bit smaller. So to divide all of them by 2 will give me a little bit smaller value to work with at the end. So I have 5 minus the square root of 3, because the 2 divided by 2 is 1, divided by 11. You cannot subtract when one piece is a radical and the other one's not, okay? Let's do one more. This one looks like it's so much harder maybe because there's 2 radicals in it, but it isn't any harder. The conjugate process works exactly the same way. So I've got 3 square root of 2 minus square root of 5. What would the conjugate for that be?
3 square root 2 plus.
Yep, 3 square root of 2 plus the square root of 5. Conjugates work the same way, whether we're dealing with both pieces having a radical or just one piece. So 3 square root of 2 plus the square root of 5. Now, the numerator, 6 being multiplied through like this. Remember, the 6 has to multiply by things that are on the outside because the 6 is not underneath a radical. So in the first one, the 6 gets multiplied by the 3 to give me 18 square root of 2. On the second one, there isn't a number in front of square root of 5, so there is actually an understood 1 there. So that's fine. 6 times 1 is 6. So plus 6 square root 5. On the other piece, again, just like before, notice that the inner terms and the outer terms are exactly the same except for their signs. So they cancel, they add to 0 on purpose. So I don't have to do the operations for the inner and the outer. I only have to do the first and the last. So what happens when I multiply, and I'll write this down here to the side just a second separately, 3 square root of 2 times 3 square root of 2. What's going to happen there? Right, so there's the 3 and the 3 make 9. Square root of 2 and square root of 2 makes square root of 4, which is 2. So 9 times 2 is 18. The first piece is actually an 18. So feel free to do a little bit of scratch work if you don't want to write all those pieces within, a long piece of division. The other one ends up being square root of 5 times the negative square root of 5. Yep, 5, and is it plus or minus? It's minus. Then in my denominator, 18 minus 5 is 13. And on this one, square root of 2 plus 6 square root of 5. I don't have like I did on the last one. I have 18, I have a 6, and I have a 13. There's no way to combine those. The two radicals on top have different radicands, so there's no way to combine those either. So at this point, I'm finished on this problem. All right, so this assignment will be due next time. We'll go over questions at the beginning, just like we have been, but do take the time to go through there. And if you haven't already been doing so because you haven't needed it, you might visit the Success Center on this one, because this one might be the first one to challenge you. We'll just see.